Hey folks, today we're going to learn about matter. The first question you might have is, what is matter? Well, anything that has a volume and a mass is considered matter. So a table or a chair or the gas particles in the air, depending on how those particles are arranged, we could have a different state of matter or condition that the matter is existing in. There are three naturally occurring states of matter: solids, liquids, and gases. In a solid, the particles are arranged in a very regular fashion, and they don't really move around a lot. They just kind of vibrate around very fixed positions, and those particles are very close. They have an attractive force. All particles have an attractive force that hold them close together, and depending on how much kinetic energy they have, or how much movement those particles have, or thermal energy, if you will, the attractive forces could be overcome or they could not be. There's not enough kinetic energy in those particles to overcome those attractive forces, so they just stay stuck together. In a liquid, the substance is warmed up a little bit, so they have a little bit more thermal energy. And the attractive forces, while they're still very strong and can hold the liquid together, and those particles together, those particles can move around and take the shape of whatever container they're in. And they're kind of very randomly arranged, and they have the freedom to move as they wish. In a gas, there's so much kinetic energy that the particles aren't even touching each other. They're very, very far apart, especially compared to the size of those particles themselves. So much kinetic energy, those particles are always moving. So when we talk about the kinetic theory of gases, we have to make some initial assumptions that help us to understand the concepts mathematically without having to go into too deep of math. So the very first thing is that in a gas, particles are extremely far apart compared to their size. So very tiny particles, big distances between them. The second one is that particles participate in what we call elastic collisions, which means no energy is lost. So when one particle hits another, whatever energy might be transferred goes directly to the other one and doesn't go somewhere else through heat or work. Those particles are moving constantly, at random, and rapidly. They're moving quickly, they're moving all the time, and they're moving in whatever direction they end up going to. It seems to be very random. It depends on whether they're hitting the walls of the container or whether they're hitting other particles. A lot of things can happen. And also the particles, in order to think about it mathematically, we just pretend like those attractive forces aren't there. In reality, they are there. There's just so much kinetic energy that they don't play an effect. They're such a small part of the energy of each of those particles that we can basically just call it zero. If it helps to visualize how these particles are moving around, I like to use the analogy of passing period in the hallways. So for a solid, it's kind of like at the very beginning of the day, before the walkabout time comes around, and all of the students are stuck right there by the doors before they can go to their lockers. They're not moving around a lot. They're kind of, in their fixed positions. They stand where they stand and wait for the bell to ring. Once that bell rings, they start to gain kinetic energy, and they're not stuck together so much anymore. They kind of flow through the hallways, and they take the shape of the hallway. And then a gas is kind of more like in the middle of class when somebody has to go use the restroom. There's maybe 2 or 3 kids out in the hallway, and they don't usually run into each other because it's a pretty big hallway for the size of the kids that are walking through. Based on those assumptions that we just made about how a gas moves around, we can come up with a couple of different laws about how gases behave. I'm going to show you the math, but we're not going to think about the math too much. We're going to be more worried about those relationships between the variables of what a gas looks like. So the first one is Avogadro's law, and it relates the number of particles to the volume of the gas. So if you think about this, if we were just to graph it, what happens to a balloon as you put more air into it? It gets bigger. So the more particles you have, the more volume your gas is going to have. That's all Avogadro's law is saying. Another law we could think about is called Boyle's law, and it relates the pressure and the volume together. If we were to graph that, it would look like this, which if you think about, as the volume decreases, the pressure is increasing. At a certain point, it really makes a turn here. So as you take a balloon that you've just filled with air, you've tied it off, as you push on that balloon, the pressure inside that balloon is increasing. It also works in the opposite way. If you have like a piston or something, and you pull that piston out, but the other side is sealed, the pressure inside of that piston becomes much smaller. The next one we'll talk about is Charles's law, and it relates the volume and the temperature together. Now it looks very similar to our first one over here. If we graph the volume and the temperature, as the temperature increases, the volume also increases. That should make sense because as the particles are gaining more energy from the temperature and they're moving around faster, they can push more on the outside of the balloon, and then the volume increases. It also works in the opposite way. If you were to take something and rapidly increase the volume without changing any of the other variables, the temperature would decrease. And the last one is Gay-Lussac's law, which relates pressure and temperature. And it looks very similar to the previous one we just did, where the pressure and the temperature are graphed against each other. And as the temperature increases, the pressure increases. The same reason as Charles's law. As the temperature increases, there's more energy among the particles, and those particles are now colliding more with the walls of the container, and they can push out more, and it has a higher pressure.